So my focus today, I want to focus really on the level 0 part of things. But before that, there are a couple of things to address before we really get to level 0. The first one is that was asked for an example of how do these things look when they look very big. And I realized that we drew this picture of in the first day, we drew a picture where we have a module. I think I do it this way. E1, F1, E2, F2, En-1, Fn-1. So this was for U prime in this case, or U was UT loop SLN. And then it became infinite by taking, I think it was epsilon Vn, and then so epsilon V1. And this would loop around like that. So this was the first example of a module which had no highest weight and no lowest weight and so on. And we can call it L omega 1. It really is for type A, it is the extremal weight module of that type. And now we can take that, I think we can, so the first thing that one of the things that we said was that we can view this as Cn. Cn is the vector space with basis V1 up to Vn. And then we take polynomials, Laurent polynomials, in epsilon and epsilon inverse, and that moves us epsilon inverse. So this looks like now a vector space in polynomials. And now if we were going to take L of, say, K omega 1, we can take L omega 1, tensor L omega 1 K times. And when we write that out, that's looking like Cn tensor K, I guess. But now I have each factor gives me one variable of polynomial. So this is very large. You can decide where the weight spaces are, where you would like to. But we have a very large polynomial ring here attached to this. That's how this extremal weight module becomes big. So I hope that such an example might help you see what it looks like. Sorry? I think in this case, I think it's actually equal, or isomorphic is maybe a better word. I think that the module. Of course, I haven't told you the coproduct, so in that sense, it means nothing. But just to give a picture of the size of it and the weights of it. So on the level of the crystal. Okay, so now I want to talk about the structure of how I picture these modules. You see, I have been fighting the whole time because I don't want to write the presentation of U. So someplace I should write the presentation, Grinfeld's loop presentation. Loop presentation. At least I find when I work in this business, of course, at some point you have to know what algebra you're actually finding representations of. And you would like to write down generators, and relations. but for many years, I didn't want to get into this business because this is a very long list of generators and a very long list of relations. And I didn't want to give it in a talk because it will take me the whole lecture just to give the generators. So I've been trying to avoid that, and I'm going to continue to try to avoid that. But at the same moment, I want to give some picture of how do I think about it. So what I need at this point is something about symmetric functions. And symmetric functions, I mean just the symmetric functions that I learned from McDonald's book. So think about polynomials and m variables, and the symmetric group acts by permuting the polynomials. And of course, one of the things is that this is a polynomial ring. So you can find homogeneous polynomials that are invariant, and the degrees are fixed, but the choice of the invariance is, there are many choices of invariance. So these are examples of this. So this would be the power sums. And this is, in the McDonald's notation, the elementary symmetric functions. But of course, you could use the homogeneous symmetric functions. Homogeneous. Or you could use, so one of the things that comes up in this Drinfeld presentation is what I like to call the Q basis, or essentially the Q basis, which is made from the first Hall-Littlewood. Actually, I have a paper with Jeff Remmel and Tamsin Whitehead about this Q basis many, many years ago, because we used this Q basis to write down characters of the Hecke algebra type A. So this appears in that setting. And again, it's used in this Drinfeld loop presentation, or a version of it is used in this. So all of these appear in McDonald's book, and they are different ways of looking at the same algebra of symmetric functions. So these are related by our favorite identities, which are generating functions, or let me use ZIU. So this is the sum of ER U to the R. Or you have the generating function for the homogeneous symmetric functions, which is this, or one way to write down a version. It's not exactly the same as in McDonald, but it's the one that is similar to what we use for the Drinfeld presentation, is you could say that the Q's are given by such a generating function. And I can view, if I'm trying to work with symmetric functions, some days I like to work with the elementaries, and some days I like to work with homogeneous, and I have methods for converting from one to the other. So this is the exponential of the sum over S of PS over S U to the S. So this kind of formulas allow me to go back and forth between these various bases. And the old paper I was talking about with Jeff Remmel and Tamsin Whitehead does that kind of analysis. So if you want to get familiar. All right, so far so good with just a little tiny bit of symmetric function. T. Yeah, so I should be viewing T as some complex number, or I should put it into the coefficient. So yeah, that's what happened. Well, I want you to think of them as the same. So either think of T as some complex number, some complex number so that it's in the base ring, or extend this to be one or the other. But all of these formulas can be done very combinatorially for these transformations. So, okay. So, all right. So now let me give a little bit of feel for Drinfeld's loop presentation. Right here. Of the quantum affine algebra without the derivation. So the generators, so I like to include the central element, even though we are soon going to set it to 1. So level 0 means C is equal to 1, but let's keep it for the moment. And let's keep the finite part of the carton, so some k's, k1 up to k inverse. And then the loop parameters, the way that we usually say it is the coefficients of the series so there are 4 series, xi plus, xi minus, q plus, qi plus, and qi minus. So this is some series, this is a sum over R in Z of xir plus u to the R. Similarly, sum over R in Z of xir minus ur. And qi plus is going to be the sum of qi r u to the r greater than or equal to 0, and qi minus u u to the r minus r in Z greater. Okay, so that's either you can write down relations just in terms of these variables, which you often see, or you can try to write down relations in terms of these series. And I don't want to write the relations for you, but I do want to stress a couple of things. So the 0 has disappeared in this presentation. So this is for I going from 1 up to n. So there's no x0. I've taken away the x0. This is the loop parameter. And these q's, we should view them as a ring of symmetric functions and this is another ring of symmetric functions. And we have one such ring for each I in 1 through n. So if you so think about it as there are n different sets of variables and n different rings of symmetric functions. So here I had one set of variables, and this was the ring of symmetric functions. And there I have n different sets of variables. And the other thing that we are doing is we are actually taking symmetric functions and an infinite number of variables. So this is Z1, Z2, and S infinity. And this is P1, P2, E1, E2, Q1, Q2. So it certainly in McDonald's book, this is standard to go to an, and we are doing that. We have somehow n different copies of symmetric functions and n more different copies of symmetric functions. But of course, by our symmetric functions game, qi plus, qi minus, can be converted if you like, if you want to change generators, to EI plus and EI minus. So instead of thinking about the Q's symmetric functions, you do some transformation to think about the E's, and that would give you a different set of generators. Or they can be converted to P's, PIR and PI minus R, or R. That's right. If we're doing, when I go to if I want to, so in some sense, it's just a very fancy way of writing down just a polynomial ring and an infinite number of polynomial ring and an infinite number of. But when I want to think of it as symmetric functions, yes, I need to do an inverse limit. And this you would find in McDonald, that inverse limit is written. Perfect. All the maps are written and then the inverse limit. But that's one of the relations. That's in all the relations which I haven't written. So I'm secretly just telling you some of the relations. So let's write some of them, because in these P's, we can really see, I love this relation, which is just one of the relations, one of the relations between all these generators. That PI bracket PL is delta K minus L times 1 on K times T to the K Cij minus T to the minus K Cij divided by T minus T inverse times C to the K minus C to the minus K divided by T minus T. Right? So theseCij's, that's the Cartan matrix. T is my quantum parameter. And C here is that central element. So what this is saying is you have some positive symmetric functions, one copy, and some negative symmetric functions, but they are tied together in a Heisenberg. Right? They're perfectly tied together in a Heisenberg. Yes, yes. It is an inherent action. I mean, this is somehow the central extension that's putting together the Heisenberg. You can normalize that. I don't view it as an SL2 action. So remember the Heisenberg group that I put up last time? It had one real vector space, which was commuting with another real vector space, and then they were tied together by an extra central element, so that when they didn't exactly commute. And that's what we're saying here, is that we're tying these together with an extra central. So inside of this thing is this big it's really big Heisenberg, but that's what we want to access. And there are several other relations. It's very beautiful to play with these. Besides the original paper of Drinfeld, there is a very similar presentation for Yangians, and it has come. This is the quantum affine algebra. So if you think about it geometrically, quantum affine is K theory and Yangian is cohomology. So the associated graded of the quantum affine would be the Yangian. But I'm writing it in the quantum affine form. But it's very similar in Yangian form. And so then, of course, there was Beck, Chari, Presley, and then it got pretty stabilized, Nakajima, I don't know, Frankel and Andes, et cetera. But it became pretty stabilized, these relations. You can look in the, I'm sure, David, you must have a favorite paper that you point to these relations. Damiani, it's a good, yes, absolutely. So it's pretty, you can look in the papers. I don't want to write them here. It'll take me much too long. Okay, but hopefully it gives you a feel that this part of the algebra is made out of two symmetric functions tied together to build Heisenbergs. And this part of the algebra will be our raising and lowering numbers. Let's see. So now I can write down the extremal weight module. So loop presentation of the extremal weight module. And now certainly I'm in level 0. And so the generators in this presentation is just a single generator, U lambda. I should say lambda, now we're in level 0. So think about it as a dominant integral weight. I'm going to use a single generator. And the relations, well, okay, we must put that it's level 0. C U lambda is U lambda. That means the central element acts by the identity. And I'm going to make it a weight vector. So Ki U lambda is T to the Mi U lambda, or I in 1 through n. And then in this loop presentation, we make it a highest weight vector. So I could write it this way, XIR plus U lambda is 0. And R and Z. And then I'm going to put some bounds on it. So E plus, so E I in the ith set of variables, EIS acting on U lambda will be 0 if I is in 1 through n and S is larger than Mi. So I'm using a special, in fact, most of the time you write this relation in terms of the Q's, but I've converted it to the E's. And when you convert it to the E's, what it says is that those elementary symmetric functions that are too long, they will act by 0. They get longer than Mi. Mi is these numbers here. So I'm forcing not to be an infinite number of E's acting non-trivial, but only a finite number of E's. And similarly for the negatives. I is in 1 through n, and S. Yeah. Of course, now we're in level 0, right? So this C is 1. C is acting by the identity, so C is 1. So this right-hand side is 0. So these two polynomial rings actually are no longer a Heisenberg. They just commute with each other. So that's somehow happening here secretly. So this is actually my favorite. In level 0, this is my favorite presentation of this model, because there are no messy formulas whatsoever. How does that feel? IJ appears because of the Cartan matrix weighting. So this is a very nice presentation, and it's the one that we start to work with. And these elementary symmetric functions are already starting to play a role. Okay. So what's the next step? So now we have built this module, which is large, which looks like this polynomial rings. Although you can see that it looks like there are polynomial rings in several sets of variables all over the. Okay. And now I'm going to build the I guess we can call it the global vial module. That's a good name for it. It has several, I think that Nakajima called it some standard something module. It has several names, but I like this one. So I remind you that C of U, we did it once before, but let me redefine it. Monic is, for me, the set of Drinfeld polynomials. And what is a Drinfeld polynomial? A Drinfeld polynomial is actually an n-tuple of polynomials. AI of U is a polynomial, which we can take to be monic. And then this lambda equal to m1 omega 1 up to mn omega n with mi being the degree of the ith polynomial. So for each lambda, I have many, many Drinfeld polynomials. All right, and now we can build a module. So then M finite A of U is L lambda with the additional condition that EI plus of U acts by AI acts on U lambda by AI of U. U lambda. Did I call it U lambda? Yeah. So what's happened? Here, these were some formal generators of my algebra. I was thinking of them as symmetric functions, but they were just formal generators of the algebra. Here, this is an actual polynomial. But if you think of these elementary symmetric functions, they were in some set of variables. Right? So the coefficients of this series, I'm thinking of them as symmetric functions in some set of variables, the ith set of variables. Here, this is a polynomial, and the elementary symmetric functions are the coefficients. The coefficients of this polynomial are the values of this elementary symmetric function. So I'm specializing each of these variables. Oh, how do I say this? Oh, R coefficient of U to the R in AI of U is ER of beta 1 up to beta mi, where beta mi, beta 1 up to beta mi are the roots of this ith Drinfeld polynomial. So the effect of this process is it takes all of those fake variables and specializes them to these actual values. All of those formal variables become specialized to actual numbers. Does that make sense? So in our first, in our example, well, we had written down something like this. that was what I gave as a suggestion of an example of what an extremal weight module looks like. Now specialize all these epsilons to actual numbers. And it becomes finite dimension. Becomes a very, how does that feel? You take this polynomial ring and you specialize them to actual numbers. The faces don't look so happy. Well, they just become actual numbers, and this is a vector space of dimension n to the k. So it smashes. If you remember in the first lecture, we had this snake module, and then we specialized epsilon to an actual complex value, and it became just a circle. So we're doing that on the same mechanics, but in general. Yeah. Oh, thank you. Local. Yes, absolutely. Thank you. And that's also called thank you. I got it. This should be where this is the global value, which is the same as the extremal weight. Equal. You think it's the which? Yeah. Okay. I mean, yeah, we should work it out. We should work it out. I have said I have several formulas, sort of one for each situation. I have a formula for the action of that series on the highest weight vector. They all are slightly different. T is my quantum parameter. U is only a formal parameter to keep track of the series. Yes. No. L lambda is global. She corrected me. She's absolutely right. This is global, and this is local. I'm sorry. I messed it up. I'm sorry. The global one has parameters, and the local one has actual values. So the local one is finite dimensional, and the global one is huge. Yeah. For the local one, because this extra relation specializes all the parameters. So maybe I can write it this way. Is that, or let me leave what I wrote. And let me write another line, which is equivalent to what I want, which is that if I take the rth symmetric function in the ith set of variables, acting on u lambda, this is equal to the coefficient of u to the r in AIU times u lambda. If I take coefficients of u to the r on this equation, I want it to be that. Good. I think good. I like the interruptions. It makes me feel better that. Yeah. All right. So now the L finite of AU is this M finite of AU modulo a maximal proper submodel. So because the same kind of old argument for Burma modules works, because this is acting now like a highest weight vector, but not for the Kac-Moody presentation, but for this Drinfeld loop presentation. But the same argument then works to say that there's a maximal proper submodule, which you can mod out by. So this acts like a standard module. And then we have what I quoted in the very first lecture is that we have, so it gives an indexing of the simple finite dimensional models. Irreducible finite dimensional. U prime, where the Drinfeld polynomial gets mapped to this called and so this is how it goes. I mean, first there was the sketch of the Yangian case from Drinfeld, and then, well, I don't know the history. Then it appeared in Charian Presley's book, and there was also a quantum paper. You did the quantum one, yeah, and the sketch for the Yangian case was in Drinfeld, is that right? Yeah, right. But you filled more details for the Yangian case in the book, right? It's the same proof. Okay, great, great, yeah. So the quantum case is the Charian. Wonderful. No, this is completely general. That's what's wonderful. The symmetric functions in general type, the symmetric functions are in there, that Heisenberg. Think about your affine Lie algebra. Your affine Lie algebra is the finite Lie algebra plus a central extension. Let's leave out the derivation. And this contains the Cartan of the finite Lie algebra plus whatever, and plus the rest of it, plus and minus and so on. But the enveloping algebra of this is already producing that Heisenberg secret. So it's really, in general type, you will see these big symmetric. Okay. Great. I have to look at that. So super. So right. So the next thing I want to talk about is crystals of these things. So I'm going to let the notation be, I want to state the result. So B lambda is the crystal of the extremal weight module, which Kashiwara said by sort of just abstract arguments would exist the way he built it. But we didn't have any, at least I didn't see in that any concrete way of building it. Presumably, I thought maybe you could use some sort of Littleman paths, or maybe, no, I didn't find a way. And then, of course, certainly the papers of Naito Sagaki, I tried to follow, they were building this crystal in some concrete way, and then there were many other ways for special types, for type A and so on. But it's not really, maybe, sometimes I think that we should change the definitions of crystals a little bit to include this case. I think I'll as I go further, maybe my philosophies will become more clear. So this will be the crystal of M finite A mu. Okay, so what is the structure then Sorry? Right, so that's what I'm saying. So in the proper, sorry? Right, but so if we go by the official definition of crystal basis, no, there is no crystal. I agree with that. However, there is a very good labeling set for bases, which we can keep track of. And so I might change the definition of crystals. We can call it something else, a pseudo crystal or something. But there is, that's right. So for the local biomodule, for all of those A mu's, the crystal will be the crystal will be the same. It has somehow very similar bases. That's what I want. So I agree. Let's definitely put some quotes here. For me, the crystal, let's just start as a basic feeling. It's a labeling set for a basis. A labeling set for some favorite basis. Doesn't necessarily have root operators, or maybe we should change what the usual definition of root operators are. That's what I'm hoping. So what we know now from all the work that's been done is that this looks in the following way. All right, so this big crystal will divide into parts like this. And K here is the number of MIs that are non-zero. Z is a set, which in my head looks something like this. It's going to be a labeling set for a basis. So it has no real structure except to be a set which is indexed by the M. Now this is on all types. In all types, this kind of a statement. So I'm writing this. This is some processing of Nakajima has a paper about 2002, which is called extremal weight models or something, and he studies the global how the global canonical bases interact with the extremal weight models, and then the many papers of Naito Sagaki, which studied. So I'm translating what their statements are. But it should be general type. Okay, so now this S lambda is the following collection of objects. So it consists of K to N tuples of partitions. N tuples. So kappa I is a partition. So I want you to think of some partition with length of kappa I less than mi. So the length of a partition is the number of rows. So I take tuples of partitions. These are a bunch of partitions. The first one must have the number of rows bounded by M1. The second one must have the number of rows bounded by M2, and so on. And this is, I like to call it periodicity. This big crystal for the whole extremal weight module is a finite crystal, I always quote, finite crystal with exactly this describes the periodicity I have again in my picture. My head, I have this picture, and then I have a finite crystal, and I have to describe the periodicity, and that's all this stuff. Is it conceptually? It makes sense what I'm trying to. Okay. So how do I? Yeah, I have plenty of time. So now let me say the next statement. Let's call this 1. And 2 is the following thing, that this B finite lambda is isomorphic to B nu plus lambda 0 W plus. All right, so what is this right-hand side? So B nu plus lambda 0 W plus is a Damasur crystal of level 1. So what do? I want to take lambda and I want to move it by some element of the affine Weyl group. So with W in the affine Weyl group. So, but first what I'm going to do is I'm going to take lambda and move it to level 1. I just physically move it to level 1. Now it's sitting on level 1. Now I can move it by the affine Weyl group until it lies in the dominant chain. So this is what we called so nu is in the alcove of level 1, and I might have to pay with some amount of deltas when I do that. Right? So J is some integer, which just by trying to move this weight into the dominant alcove, that affine Weyl group will introduce some factors of delta, and they are whatever they come out to be. Right? So that tells you, starting with the lambda, you obtain this W and this nu. And what we're saying is that this crystal is the same as that crystal, which is
this local Weyl module is bigger than the Damasur module. It's in the non-simplified case.
okay.
So this crystal will be too small for what you're trying to.
All right. We'll have. Yeah, you should explain me the example. This is certainly always. So maybe I'll just make, while we're here, I'll make a remark about how this. Conceptually, what's happening in my head is that I take this M finite and I tensor it, say, with L nu plus lambda 0. So this is a level 0 thing, and this is a level 1 thing. And inside of here, I have the highest weight vector for that. And then I have vectors in here. So I get some piece. This is sitting inside of some level 1. And the problem is to identify what is that piece. So in some cases it's right, and in some cases it's not right. Is that? In the simply laced case, it's okay. So let's put simply laced. So that gives me the A1 is the alcove on level 1. It's the alcove on level 1. So when we took W orbits, we took representatives of the W orbits. These are the representatives of the W orbits that we chose on level 1. Okay, wonderful. So then and finish with what I want to talk about, the characters here. So in this simply laced case, if I want to compute this character of this de Mazur model, which will be that character of that B finite, as this is given by applying de Mazur operator. Said we had de Mazur operator, and that will compute for me the character. And then Jae-Hoon explained that if we in level one de Mazur operators, match with specialization of a Cherednik intertwine. Intertwiner on the polynomial surface. In this special case, when the de Mazur operator is in level one, and you look at the polynomial representation intertwiner, then they match. And so it's a beautiful calculation, actually. And so that tells you that this character on the zero can be identified as a non-symmetric Macdonald polynomial, specialized. Depending on how you do it, infinity or zero, there's two ways to do it. In my paper with McGlade and Young, we did several examples so you can see what the difference is. And this is also equal to, at this specialization, there's another statement that this is equal to a non-symmetric Macdonald polynomial special. But which is a nice statement. I mean, because I love Macdonald polynomials, I like the fact that we can state that. But in principle, we can just, both methods are essentially computing the object by applying de Mazur, whether you call them intertwiners or de Mazur operators. There's, all right. Now this W is a very specific W. It is exactly the W which moves this thing into the dominant chain. So that W is actually not part of the data, and neither is the nu. Only the lambda is part of the data. So that gives me that part, which is this B finite part, and then I want to look at this other part and its character. So what we want to look at is what I call RG lambda. So this is polynomials now. So I have various sets of variables, but I'm going to label them. Instead of, I've been writing the sets of variables, the first set of variables with a superscript 1. I've been writing it like this. But because I want to put plus minus 1, I'm going to put the 1 in the denominator. So that's one set of variables, symmetric functions. And all the way up to the last set of variables, symmetric functions. Remember, I had a whole bunch of symmetric functions rings, one for each set of variables. And then we said that if M gets too large, it vanishes. So I don't have I don't have to take an infinite set anymore because I'm at a specific lambda. So I take M1 of the first set of variables, M2 of the second set of variables, and so on. Okay, but now if I look at this, let's just do a single case. And I write this in terms of symmetric functions, then these are polynomials in EM plus minus 1 and E1 up to EM minus 1. Because of those plus minus 1s, I get a ring like this. And this, or I could write it even better, I could write it. So what is the character of this object? This is, well, you can see that this forms what I call a Z. So this is 0q to the m. 0q to the m is something which was a delta function in unstock. So this is q to the minus 2m, q to the minus 2m, q to the minus m, q to the 0, q to the m, q to the 2m. So this is a sum over all the integers. So this in a crystal form, this is one of the Z's. I have all of these copies of Z's, and so I'm going to have several copies of Z. In crystal form, it's just a set indexed by Z. In character form, it's this series, which if you want to do it properly, you do it the way An did it as a delta function. And this part is the product, k going from 1 to m minus 1 of 1 over 1 minus q to the k. Because this E1 has degree 1, E2 has degree 2, and so on. Okay, so now we can sort of put together the character of the whole extremal weight module as the character of that de Mazur piece, which looks like an element, a non-symmetric McDonald polynomial specialized, times the product I going from 1 to n, and then I'll have 0 q mi times product k going from 1 to mi minus 1 of 1 over 1 minus q to the k. Right? So because this part, this is the character of my z to the k cross s lambda. And this part is the character of my b finite lambda. And altogether, I get the lambda. So that's what it looks like. Of course, when you multiply a bunch of zeros together, you can see that this is a priori some horrible thing, but with the crystal, we can sort of work with it. Okay. So I'll stop there. Yeah, I don't really know, but the experts are here. It's not. Do you know what it is? It's bigger than the de Mazur. There is no. It has a flag, a de Mazur flag. So I guess it's known what the structure is, but it's not exactly what I wrote, unless it's simply So you can certainly do symmetric functions for other vowel groups. I don't know if they have anything to do with quantum affine algebra. A priori, those symmetric functions are entering just because of this Heisenberg, which is just the Heisenberg. Yeah, everything is infinite. So I don't multiply them. I just keep track of which crystal basis element that term corresponds to. I think as a function, it's not something you work with, but you can keep track of the crystal basis elements and what's happening as they move.